folks. So the purpose of me making this video is to help you better understand what's sometimes called gravitational acceleration. And hopefully you've watched the previous video that showed the feather demonstration, the feather and the nickel in the tube. And the important thing is that when the air was evacuated from that tube and the tube flipped over, that the feather and the nickel accelerated down at pretty much the same rate. And that rate is referred to as gravitational acceleration. And the gravitational acceleration in metric units is about 9.8 meter per second or meter per second squared. Or in English units, this is about 32 feet per second squared, or feet per second. So I want to kind of walk through a quick example with you here of how gravity affects falling objects, as long as their mass is relatively large compared to their surface area. So I'm not talking about things like dropping a beach ball or a feather. You know, imagine this person at the top of this building dropping a relatively dense object such as a rock. So the first thing we do when kind of analyzing this is we would draw what are called motion diagrams. And the motion diagrams I like to visualize like a digital camera taking snapshots in time. Click, 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 then superimposing all of the pictures. So as time goes on, because the rock started with no velocity in my example at t equals 0, it's hardly moving yet. As time goes on, however, it's going to increase speed at about 32 feet per second. So the motion diagram might look something like this. And again, the distance between the rocks illustrating that the rock's moving faster and faster and faster. I could also include some velocity vectors during some of these time frames. And if these are velocities, I should label them as such. V, V, V. And again, these velocity vectors would be increasing in magnitude because the speed of this rock would be getting higher and higher and higher. So we're going to actually attach some numbers to it, and we're going to talk about after 1 second. So after 1 second, or I'm going to put it at t equals 1 second, the velocity of that rock is going to be about 32 foot per second down. I'm getting that basically right from this. Acceleration is delta v over delta t. I'm using 32 for the acceleration, 1 second for my delta t, calculating the change in v there. So after 1 second, rock's going 32 feet per second. Now, the acceleration of 32 foot per second means that every second that goes by, that velocity is going to change by another 32 foot per second. So at t equals 2 seconds, the v is going to go from 32 to 64 feet per second. And at t equals 3 seconds, now the v is going to increase by another 32 feet per second, so now we're going to be at 96 feet per second, and so forth. So what gravity is essentially in this problem is it's the rate at which the velocity here is changing. And that rate is about 32 foot per second squared in English units, or about 9.8 meter per second squared in metric units. Now, one of the things that comes up in physics is plus and minus signs and dealing with that. So acceleration is an example of what's called a vector quantity, and a vector quantity is a quantity that has magnitude and direction. And the way we communicate direction mathematically is by using coordinate systems combined with plus and minus signs. So if I were to put a coordinate system maybe like this, x, y, the motion of this rock is what I would call in the y direction. The x coordinate of the rock is not changing. The acceleration of the rock is down, but I've got the positive y-axis pointing up. So in a coordinate system such as this, I would say that the acceleration numerically is minus 32 foot per second squared in English units. The minus sign indicating down in the negative y direction. However, we could also express the acceleration in a coordinate system that maybe points something like this. There's nothing wrong with putting the plus x or plus y direction down. And in this example, since acceleration is down and I've got the positive y direction pointing down, now I would say, all right, the acceleration of gravity is positive 32 foot per second squared. So I think the point I want to make is that the plus or minus sign on gravitational acceleration, or any other acceleration for that matter, is really meaningless until a coordinate system is defined. In general, positive accelerations mean acceleration is in the direction of the positive direction of the coordinate, and a negative acceleration would mean the acceleration is in the opposite direction of that. So anyway, until a coordinate system is defined, a plus or minus sign on gravitational acceleration is somewhat meaningless. So hopefully this video illustrates a little bit, just a little bit. It's just meant to be kind of a wee introduction into gravitational acceleration. I'm going to make more videos about how to solve physics problems involving gravitational acceleration. So hope you've enjoyed it. Have a nice day.